Let's get started. Okay, so first of all, many of you probably know, but I think it's good to spend a few minutes here. So what is the NanoIC Pilot Line? Well, NanoIC Pilot Line is one of the 5 pilot lines currently existing in Europe, made by a consortium of different institutes. We have imec, of course, the CFET, the Fraunhofer, Tyndall, VTT, and the CSSNT in Bucharest. This pilot line has a specific focus, which is the one to provide Europe with a beyond 2 nanometer leading edge system on chip pilot line. So we will present and propose to Europe a certain set of technologies which are quite advanced, let's put it like that. And they are meant to cover part of the technology aspects that will take place and develop even more in the next future. We have 3 main pillars in terms of technology. We have advanced logic, novel memories, and advanced interconnect. Each of those pillars, it is actually divided in more sub-activities, if you want. I will go in details to that. But what is important to mention is that associated just with the technological and scientific development associated to that, we have a program, if you want, that encompasses several other actions and activities. Specifically, we have a program of infrastructure update, which is taking place here in Leuven. We will enable, and we are enabling already, fabrication and opening of the pilot line. So capacity and the capability to fabricate towards the smaller nodes and towards technologies which are today very challenging to fabricate. In parallel, we are, of course, developing every single process steps and process module in order to make those technologies available and somehow open to the public, which is ultimately the scope of a pilot line. To do that, we are working, we worked in the last year and a half on a very clear and straightforward access and selection process. Today, I will talk a little bit about it, of course. And of course, in parallel, there is a very large activity concerning education and workforce development, which is an entire work package. We give to that a very large importance in the NanoIC Pilot Line because we believe that the pilot line covers a very important task today, bridging a gap that it exists in Europe and that we need to cover in the next 10 to 20 years. That's really fundamental. For the pilot lines, as I said, NanoIC is working on, let's say, very advanced node. Other pilot lines are covering also different technologies. CFET works more on the FD-SOI technology. Fraunhofer is more on heterogeneous system integration, although some of those technologies, as you'll see, are covered a little bit in all the pilot lines, but in different flavors. Let's put it like that. So what's behind the idea of the pilot line or NanoIC, and generally speaking towards future computing system? Well, you have seen probably a version of this cartoon already in many other contexts. What I want to briefly, I hope you see the pointer or the mouse. What I wanted to just talk to you a little bit is what NanoIC is doing. Well, we are focusing, as I said, on advanced logic nodes, meaning 2 nanometer and beyond 2 nanometer down to the CFET architecture. And today, we expect those little chips, these very advanced little nodes, to be somewhat part of what is defined as chiplet architecture, or an assembly of different chips that are communicating each other and exchanging data, exchanging information, signals, if you want. The logic is just one part of it. And of course, there are good reasons to do that. One reason is definitely the fact that processing small dies brings you an advantage in terms of defectivity control, but also, of course, cost. That's clear. Smaller nodes need a very advanced process, which are very expensive. So smaller nodes, smaller chips will be automatically cheaper if you want. Of course, one way that's from the business, if you want, and the fabrication perspective, but also from the device engineering perspective, today we see that we are in the need of moving towards new concept for continuing the scaling process. Reason is there is a clear bottleneck. It's called the memory bottleneck, right? So we need to make sure that today we are able to connect logic and memory together. Today, the logic is not anymore the bottleneck. The bottleneck is towards the memory. One way that we envision, and it is somehow worldwide envisioned, how to connect this to and to overcome this bottleneck is to create those type of devices that you see in the picture. So one single device, which is actually split over different chips. One part will be, for example, the logic that we are developing also, of course, in our fab. I will go into detail later. And then there is another part, which are high-performance memories, which are sitting on a different chips. How do we make sure those devices are talking properly? Well, that's how one big pillar of NanoIC, which is the interconnect. There are many ways those different dies can talk each other. And I will go through at least two of them today. Possibly there is even one third that will happen in the future, but I will talk about later. Finally, how to power those systems. Well, in the picture you see here, those dies are sitting on top of photonics because that can be one efficient way and very fast way to exchange signal. To do that, we are also developing the integration of gallium arsenide quantum dot laser amplifier directly on chip. So how to stack it directly and deliver power to all your different chips. That's also covered in NanoIC. So in terms of let's say innovative technology here in NanoIC, we are offering two different type of way to access their let's say the design, if you want. There are what we call design pathfinding, which are dedicated to explore innovative design conditions and solution for extreme nodes, 2 nanometer, A14, A7, and so forth. Those devices are, those PDKs are not meant to really deliver physical chips to the users of the pilot line. But of course, collaborations and theoretical exploration of those models are all included. And let's say this represents today one of our, let's say, stronghold, if you want. It is really what you can see, for example, for our N2 PDK, a PDK that we released already more than 1.5 years ago to the public, and will soon be updated to a new version. And that's concerning what we define as pathfinding. Of course, that will be extended also to the other technologies I talked to you before, which is memories and interconnect. We'll come to that. On the other hand, we have what we define as system exploration PDK. Those PDKs are the ones that are going to be able to deliver physical wafers, physical material and silicon to the let's say users of the pilot line. Here we will be able to create MPW, let's say in collaboration with, of course, all our users of the pilot line. This will be available today. It's already available to all European, let's say, stakeholders, which can be SMEs, startups, academia, and so on. It is very important, as I said, to stress that all these activities are just part of the access. But I believe that, as I mentioned before, we are in a clear gap today, and we need to make sure that our future, let's say, people that are working on those tasks are really up to speed, if you want. For this reason, the NanoIC Pilot Line is providing to the community a large number of activities that are covering PhDs, PDK training days, internships, and even expert courses for, let's say, more towards the expert workers. PDK workshops and trainings are today one activity we are really looking with a lot of interest, of course. We have already had for the N2 PDK quite some successful events here at imec, and let's say we are really proud of what has been and also what will come, because we will do that for all the technologies. All the memory and all the interconnect will be offered to the public first towards simply download of the PDK, and then also with training event that we keep typically twice a year. That's more or less the frequency. Let me go a little bit more into detail what NanoIC, how the NanoIC plays a role in the chips GU. Well, you have seen already, actually a few minutes ago, probably this picture. This is how Europe has envisioned the role of the pilot line in the chips GU. Together with design platform, the two play a role like an engine, if you want. They are the one that are moving forward the chips GU activity. This engine is actually, as I said, composed by the pilot line, but also a very important element, which is design platform that is supporting you and will support users accessing all expensive EDA tools and design libraries and all these softwares, which are very difficult to access to the public. But of course, the two will exchange. They will be somehow complementary one each other. Today, I think the very important step we need to look forward is to how include people to work with both the design platform and the pilot line. And for this reason, I believe the competence centers are a key factor. You see, actually, one way among the two that you have to access the pilot line, it's indeed through the competence center. We look through that. We look at that as a let's say a hub that will connect on every single territory in Europe the local expertises and will funnel that towards the pilot line. Of course, we plan to be present on each country with dedicated workshop and sessions, even more, of course, in the next and upcoming months and years, in order to present to the public and to all the stakeholders what are our advancements and how can they really work with us. So this is really the role, a fundamental role in my opinion, because pipelines per se are infrastructure that we are building, but of course we need the users to the pilot line, and that's where we want to interact in the most complete way with the competence center. That's really what we are trying to do in all Europe. We have been already in the different countries, Netherlands, Ireland, a few weeks ago in Portugal, and today I'm really pleased to be here today explaining a little bit what's the idea behind. How really we foresee this NanoIC journey. That's how I call it. So this path is actually starting for users and for our technology expert with what we define as PDK development. So for both, for all the three technologies, advanced interconnect, the embedded memory, and the advanced logic, meaning only path finding, we are, let's say, in the whole team, the whole PDK team is actively working in the development of such design environment. And as I mentioned before, we released already previously advanced logic. So 2 nanometer PDK to the public is downloadable for free by through Europractice actually, but also you can directly look at it in one of our courses that we offer, as I said, twice a year. We will offer that also for interconnect and the embedded memory. This is part of the, let's say, only the beginning. Of course, a crucial part is the training for this design environment. We want users, which can be as of master students, if you want, people that are interested in knowing new technologies and learning what are doing the big fabs, what are doing the real foundries, and what are we going to have in our chips, in our devices in 5 to 10 years from now, to 15 years from now. Well, for all of that, we have specific training activities, webinar, like the one we're having today, and also dedicated workshops. That's a fundamental part of the NanoIC journey, if you want. As soon as our PDK has reached a certain maturity, so we are confident that the flow can deliver the expected result, we are going to open the pilot line together, of course, with all our consortium partners. And that's where our customer engagement will start in the more, let's say, in a more intense way. To do that, we plan to have a series of outreach activities involving the chip competence centers, the design platform, the other pilot lines, and of course also presence at very, let's say, in a very large number of events and conferences. Here, of course, we need to stress the interaction between the competence center and us. It's also thanks to the access community, which are somehow coordinating all of that. The EuroCDP, of course, will also play a role because pilot line will work together with that. And we expect, of course, the other pilot lines, the Apex, the FAMES, the WBG, PIX Europe, to be part of this customer engagement process. Once that, of course, started, the most straightforward way to interact with us will be through simple MPW services. And of course, that will engage, of course, the customer in a standard design process that can take necessary time. And of course, all the fabrication will take place in our pilot line. It is important to state that as of today, our PDKs are not yet ready for that, but soon, I believe already next year, we will be already sharing news about it. Of course, not all the technologies will be available immediately. That's important to state. We will release technologies as soon as, let's say, they are ready. Most likely, we will focus first on advanced interconnect, which I will explain you in a moment. So here we go on technology side. Well, as I said, we have three different pillars. And the first one I want to stress is the advanced logic. Those PDKs, which I'll go in detail in a moment, are targeting 2 nanometer, as we already released today, to the public, A14, A10, and then the CFET architecture, which is really a gigantic step forward into fabrication complexity. I'll show you a cross-section in a moment. It is really impressive. All this PDK on the logic side will be provided to the public for free, as I said, but they will be virtual, meaning you will not be able to fabricate the devices with that. Of course, those PDKs are corresponding to physical devices that we fabricate in our pilot line, that we test electrically, and of course we use to benchmark also the PDK, but we cannot offer that to the public at the moment. The novel embedded memories will be actually instead focused on specifically 2 different type of memory, which are the spin orbit torque MRAMs and the embedded DRAM memories. For those, we foresee specifically for the EDRAM, we will open the pilot line for fabrication, while for the RCT MRAM, we will keep it for the time being on, let's say, on the side of a virtual PDK. For the advanced interconnect, there are actually 2 main technologies, which recently got the inclusion also of silicon interposer. There will be 3D die-to-wafer hybrid bonding and 2.5D RDL redistribution technologies. I'll show you in a moment. First, let me spend a little bit more time what we have developed in the last years in terms of N2 PDK. So today, the N2 is a technology based on nanosheet devices, so gate-all-around transistors. As of today, we have a standard cell library of more than 100 cells, abstracted layout views, GDSI layouts, and so on. All of this PDK can really provide a user with a very large experience if you want. It has timing power views, multi-threshold voltage, standard cell spice, netlist, VT corner support. All of this, it's actually cited by a very important technologies, which is the backside power delivery network. This is something that will be the backbone of the future technology node due to the fact that power delivery will become more and more challenging the more we go down in dimension, if you want. Soon will be available SRAM micro integration directly on the PDK, on the N2 PDK. We will extend the VDD support, and also we will keep on, this is actually a routine activity, updating our ticket models also with temperature scaling. All these devices have been already published by our science department, and here you have just some of the references if you want, but of course I'm very happy to give you more insight later or in any type of communication you want to have. As I was saying, you can download already today the PDK. There is a free access, of course. As usual, what will happen is that when you try to download the PDK, of course, you will have to sign what we call DKLA, Design Kit License Agreement, which will somehow establish a, let's say, an NDA between us and you as a user. And other than that, the PDK is immediately available for all European stakeholders, while for non-European stakeholders, we have a procedure in place with the EU, and we are routinely asking for access to also non-EU institutions. So why we do that, actually, that's something that I would like to probably spend some time, because such advanced nodes are really complex to fabricate, and we need to understand why actually we are taking this challenge in front of us, why we need that. Well, today we are, as I said, approximately at N3. We foresee some foundry releasing N2 already next year. But as you see, there is actually a change of slope here. We are not able anymore to follow the transistor density scaling curve. And how do we do that? How can we try to cope with that? Well, it is already known that we will slow down somehow. The density will somehow not grow as expected. But to keep a certain growth, we will need to access to really fabricate different technologies. The first one will be indeed nanosheet. Then there will be similar technology. It's called forksheet coming out. But then the last one will be indeed the CFET architecture. Other than that, we are looking more towards 2D materials if you want, but that's really the next step. As I said before, this technology, this PDK, and of course also fabrication in our line are already ongoing since approximately September 2024. And of course, it is continuing and will continue till the end of the project, which, by the way, it's on in 3 years from now, it's on the 2028. How do we enable a PDK for such a complex technology? Well, it is clear that we have seen it already in previous nodes, but today even more, we cannot continue scaling just through miniaturization. We cannot keep on scaling down devices physically. First of all, it's going to hit somehow atomic level limitation, but also from the fabrication point of view, the improvement and from the device perspective, they will be very limited. For this reason, we implement what is called design technology co-optimization. So we look at the system from an holistic point of view, so from very different corners, and we try to combine different technologies in order to continue the scaling of the performances. This goes through an extensive device modeling that enables us to design cells libraries which are competing with, let's say, foundry level, commercial foundry level results. Specifically at imec, the design enablement process is divided in 3 different phases. So starting from the left, we go from what generally called device modeling, and we base our device on a TCAD based. So we calibrate our TCAD model, our physical silicon model on real devices, on physical devices. This is fundamental to keep, let's say, solid roots of our technologies in real silicon. Based on that, we are then able to build technology upon it, and we can always benchmark the results that we get with our simulation. This is fundamental. Otherwise, we would not be able to make meaningful simulation, right? Once we start to build our transistors and, of course, all the metal stack, we are then able to go to the process of parasitic extraction that we do through standard tools like Synopsys, Rafale FX. This is a process that takes always place for our PDK, and is, of course, also fundamental because it's one of the most important parts of a CMOS PDK. These devices, once they are characterized from, let's say, a basic point of view, are then tested on basic concept, on basic circuits, like for example, enhanced ring oscillator, and we try then to see how those oscillators are performing compared to what we expect from a design point of view. This is all let's say a continuous exchange between fabrication and design, and let's say fabricated design and theoretical design. So this is really a fundamental part of the PDK creation, if you want. Once we are happy with how the devices are performing, then we go one step further and we start to create our cell templates according to what we have today as little rules. As I said, we benchmark our devices with real devices, so we know what are the little rule, the limitation we have in a standard fab, in our fab, of course, in the NanoIC labs. And then we make sure that those are translated into standard cells, up to 140 cells that we have today, also together with memory compilers that we have today in the N2PDK. This intermediate step is then preliminary to what comes afterward towards the definition of all the PDK standard file, like the liblef, techlef, where all the technology files are included within the PDK. And those files indeed are available to the public then to open for design benchmark. This is really the basic for any users to interact with our PDK. We use standard tools to do that, like Cadence, for example, and of course also Synopsys. These are, let's say, our standard interaction with our PDK. And to be mentioned, in our trainings, our PDK trainings are that we host at imec twice a year. We have an entire day dedicated with a certain number of computers available for PDK testing, together with our R&D expert, where people can really design and be helped by our R&D expert using Synopsys, using Cadence, using all standard EDA tools available, and implement our N2PDK place and route exercises there. So that's really the core of the PDK activity, and all of this will be expanded and extended over the next technologies, as I said, up to the CFET architecture. Let me go a little bit through let's say, physical result we have on our devices. We demonstrate already in our fab nanosheet FET. So we have test vehicles ready for module exploration and different process steps together with materials and tool suppliers. These are the results that you see here. These IDVG curves are already published in the LSI last year. And on the left-hand hand, you have a cross-section of, let's say, TM of our device. You have our stack of different nanosheet, which are, let's say, sitting over a pitch of 48 nanometers. So you can imagine we are really going towards very tiny dimension here. This is only one part. But very recently, always last year, we released the first backside contacted CFET architecture device. This has been also electrically measured, as you see here, released in IDM. These devices are another level of, let's say, new order of complexity. We stack NFET and, let's say, NMOS and PMOS vertically here. We are talking about an order of magnitude more of complexity, but as it to be noticed, those are backside contacted. So those are really looking forward for, let's say, the new way chips will be fabricated in the futures. Some words I need to spend on memory now, which is a very important part for the technology. The first one I want to talk about is the EDRAM technologies. So those type of memories are actually based on a new concept called two transistor zero capacitor. Those are two interlaced transistors actually that are combined in a smart way in order to, let's say, store information. Those devices are already physically fabricated in our fab. We have released a paper this year in a conference. And for this technology, we will offer PDK available for all stakeholders, so academia, large enterprises, SMEs, startups, and device demonstrator, of course, accessible to the public. These memories are now considered one of the most promising candidates for AI application, generally for all energy consumption, let's say hungry energy applications. And today, I believe we are really offering something cutting edge to the public, and hopefully soon we will open that to fabrication for all the community. The second memory technology that I want to discuss with you today is this, what we call spin orbit torque MRAM. So we're talking about storing information in magnetic layers over the back end of line, over standard CMOS devices. So on the right-hand side, you see here pictures related to our test chip, where we actually implemented those memories over a certain metal level over standard CMOS. This is, I think, metal 4. And you see here in the TM all the different metal stack. We already see good read and write and retention properties. There are some challenges ahead concerning the writing current. And for this technology, we will offer definitely pathfinding PDK, so exploration PDK, and also that will be available for free to the public. Hopefully, that will happen already in the upcoming 6 to 12 months. The last part of the technology I want to talk about developing NanoIC is a very important piece of technology that, in my opinion, will cover a lot of the devices that we will have in the next in the next future. There are, for example, also the other pilot line, Apex, which is working on similar concept, but I think this is really where Europe can play an important role. We are talking about the die-to-wafer hybrid bonding with very tight pitch interconnect. Specifically, in the NanoIC, we will offer PDK and fabrication to the public for 2-micron pitch interconnect. Today already, you can also look at our electrical data. We can offer 90% yield on daisy chains. So basically, what we do, we take electrically active wafer and we stack chip on top through copper-copper bonding. This is an extremely challenging process. We have a topography variation required over the copper, which is, let's say, less than 1 nanometer per micron. Above that, you start to not bond anymore properly. You have then a standard die filling with oxide, and then this wafer, it becomes somehow a solid device. And then, of course, you can connect electrically your die through silicon via, if you want, for example, in this case. This technology, as I said, will be soon available to the public, I think. First, of course, we'll release PDK and then, of course, training and then fabrication to the public. The last technology I want to talk to you today is what we call fine pitch redistribution layer. This technology is another way, if you want, to combine different dies from the electrical point of view. Why we would do that? Well, there are different ways to requirements sometimes. That all depends by the pitch between the metal lines. Some assembly requires extremely tight pitch. Some of them, they do not require that, and you can use standard assembly technologies like solder bumps and so on. But for some technology, you need really to go, let's say 100 nanometer or few micron pitch. Well, that's one we have seen before with hybrid bonding. And now instead, we are showing you another type of assembly, which is based on, let's say, the creation of a interface stack is what you see here in yellow. So you have an organic patterning layer, a bit like a resist if you want, which is then filled through a standard damascene process with copper and then CMP. At the moment, you can create, I think, up to 5 levels, if I'm correct. And of course, you have quite tight pitch. You have 1.3 micron metal with interconnect, and you can assembly on top of it by a standard solder bond, for example, bonding 20 micron pitch die to RDL bonding. This technology will also be offered first as, of course, PDK, but also fabrication and open to the public. Of course, for these last two concepts, the access to the public will be somewhat let's say, more to be defined. Reason is, of course, people will come with their device. We will offer fabrication steps here to combine device. But of course, there will be different type of device that will need to be combined through this die-to-wafer bonding approach. So also here, the access will pose to this technology will pose significant challenges, but I believe this will be a very important part of technology that will be developed in Europe in the next years. And that's, I think, something we can really play a fundamental role. And generally speaking, being a technology with not dealing directly with the front end of line, also the cost will be somehow reduced respect a standard CMOS process. Just I want to mention a few last things, how our training are normally done. We have a first day where we introduce the nodes. In this case, it's the N2 node, then can be the same for memory and interconnect. And a second day, we do a full hands-on with the idea tool usage and so on. Just for you to know, we will do the next event on March 2026. We will announce the precise day soon. And also, just to mention what we are currently soon hosting will be the winter school here will take place at imec. I think it's going to be mid next week. It's already fully booked this year, but we are already preparing for summer 2026. There are on our website, the NanoIC website, several opportunities already available. Please have a visit there, have a look. And don't hesitate to contact me for questions. Thanks a lot.